Hello, Annie. Are you getting the hang of unicorn horn yet?
No. I can't wait to be rid of this thing. I managed to turn one of my sofas at home into a crate of beets. I don't even like beets. The unicorn is supposed to be back from his vacation tomorrow, and it's not soon enough.
I'd be happy to take that horn off your forehead. It would be so amazing to have a unicorn horn.
You'd like it for about 5 minutes, Bojan.
No. I'm sure I'd love it. Real magic.
I'll tell you what. If I can figure out how to transfer this horn to you, you can have it until the unicorn returns.
Oh, goody.
This season of the Bug Hunters Cafe is made possible by Soft Terrific, Mousepaw Media, and what are you doing?
Trying to learn to play the trumpet.
Don't quit your day job just yet.
Just imagine me with the unicorn horn.
I am imagining it, and I'm feeling compelled to double-check my health insurance coverage.
Nonsense. I'd be great at it. I just think about what I need and poof, there it is, in ice cream form.
Or poof, I'm a turnip. Remember what happened the other day?
Ruin hardly noticed being a plant.
He's still finding potting soil under his nails. Well, hopefully nothing strange will happen with this week's guest. I found out about Itamar Turner-Trauring because of his Eliot logging library in Python. He's working on Sciagraph, a SAS to help identify performance and memory bottlenecks in production Python data. He's also a consultant and writer at Python Speed, and he loves talking about all the mistakes he's made in code.
He should be fine, and he hasn't turned anyone into anything in at least 3 hours. And besides, she knows how to reverse it. Oh, hi, Itamar.
Hello.
Hi, have a seat.
Thank you.
Can I get you anything to drink? The coffee's on Soft Terrific and Mousepaw Media. They sponsor these talks.
Sure. Decaf latte.
Decaf latte. I will get that. And your usual Bojan?
Espresso without coffee with extra rainbows.
Absolutely. I think they have double rainbows today, so I'll get those in there.
Sounds delicious.
I'll be right back.
So, I have a question. Why did you develop a new logging library?
I was working on a distributed system which had sort of grown organically, and the code was very complicated. And so just understanding what was going on was very difficult. And one thing that is missing for most logging systems is that they just give you points in time. So this thing happened, this thing happened, this thing happened, this thing happened. And so it's very hard to trace causality. And as soon as you're doing something that spans multiple processes or computers, tracing causality becomes even harder because if you have different computers at the times might not even be in sync. But also just because something happened before something else doesn't mean it was like correlation does not imply causality. And so I wanted a logging library that would give me causality. And so unlike logging, tracing systems, which is what Eliot is, and now are becoming much more popular, have information structured as spans or actions, and a span has a beginning and an end, and it can start other spans, and so you end up with this tree, and the tree basically gives you the causality because you can see this span was started because of this span, and so those spans, if you do it right, can span different processes, and so you get a much more rich set of information about your process than you would if you're just doing sort of these individual isolated statements.
That sounds pretty amazing. And in the name of all the programmers who had to stay on call during the evenings, I'm very grateful to you.
As a library, it's sort of Python only and it's sort of limited, but these days open telemetry is a standard for doing this that supports multiple languages and has like integrations with a whole bunch of frameworks built in. And then there's a whole bunch of companies you can then feed your data to. So this is sort of a much more widespread idea with which like sort of significant implementation and significant tooling. And so for people who are into this sort of thing, open telemetry is like the sort of industrial scale version. And the version I'm working on, Eliot, I don't have a lot of time for. I still maintain a little bit. It has some nice things for scientific computing in Python. And it's, I think, nicer for like smaller programs. You don't need to run a server, for example. Open telemetry is, APIs aren't quite as nice. And so Eliot is sort of the same idea as open telemetry, but for a smaller scale and Python only.
Here's your coffee, Bojan, and here's yours, Itamar.
Thank you.
And I've got a double tall caramel macchiato because I love these. So I caught part of that. So I've actually been using Eliot at work and really enjoying working with it. But I have kind of a confession to make that for me, and I've noticed I'm not alone in this, but for me, when I'm working on my own projects, I tend to treat logging like a feature rather than as an architectural decision. And I would guess that that sort of afterthought mindset would lead to bugs. Would I be correct in that assumption?
I mean, not necessarily. Like logging it's a solution, one solution to a much bigger problem, which you can approach in other ways. Much bigger problem being the software we write, we can know what the inputs are and we can know what the outputs are, but there's these vast swaths of intermediate states that are completely opaque. And so that is where the complexity of software comes in. And sometimes those states aren't even in your software, they're external. I can tell a fun story about that. But logging is one way to deal with sort of post facto understanding those intermediate states. But there are other ways to understand those intermediate states. You can have tools that will just effectively track every single thing your program does from beginning to end, down to machine code instructions. So there's a time traveling debugger called RR, where if you identify a problem, you can actually go back, you can go backwards and see all the changes led up to it, like CPU instruction by CPU instruction even, is my understanding. Or you can say, I'm going to do things that will make my intermediate states smaller and more understandable just by reading the code, and so on. So logging is one way to deal with this, but there's other ways as well.
Another way, also acceptable, is to just sprinkle print statements through the entire code base.
I mean, that's logging, right? It's very simple logging, but it's logging. So I feel like it falls under that particular domain where you're saying, I'm going to emit some information that I think is useful. Whereas you can think of, let's emit all the information, or if you're doing statistical profiling for performance, it's going to say, I will tell you what was happening every n milliseconds. But whether or not you think it's important is up to you, and it only tells you about slowness. So like there's printing and something like open telemetry are in a spectrum, but they are still you making a decision that this is something important to emit. And so fundamentally, I feel they're the same.
You mentioned that you had a story about intermediate states being external to the code.
Yeah, so I guess a little bit of random context. The reason I'm drinking decaf is because I used to have very bad RSI. And so for a while, I was sort of not really programming. I was sort of doing product manager and sort of things that involve less typing. So this story happened at that period. And then once I got better, and then I was sitting on an air conditioner, and my RSI came back. And so I figured out that like being cold or bad circulation makes my arms hurt when I type, which is a good thing to know. And so I figured that caffeine would probably have the same effect because it shrinks your blood vessels. And so I just avoid caffeine so I can, on the theory that it'll probably make my arms hurt. So I was working on this large-scale project, an airline reservation system. And so there's a bunch of different teams working on a bunch of different servers. And one of our test environments, like a query started timing out, talking to one of the services. And it was not consistent. It was intermittent. And this was like a test system, so there's nothing under load or anything. Like people would manually do some transactions, like a test reservation. But it was timing out. So I went and looked at the logs, as one does, and there was a hole in the logs. So during the time when there was no response, nothing got written to logs. And then afterwards, there was more logging. So something had happened where the process was sort of paused. And it didn't seem like it could be like overload from the CPU because this was the queries weren't particularly exciting. And again, this was a test system. It wasn't, the query volume was minuscule. Like these were like super optimized C++, got to return the queries like as fast as possible. Like these things were fast and they were robust, and this thing had been in production elsewhere for years. So I thought about why would there be sort of this gap in the logs? And so my first thought was writing to disk is slow for some reason because the logs are on disk. And so if somehow writing to disk became very slow, you would have a gap in the logs. And so I wrote a little tool, and because I wasn't typing very much, like I could do like 5 lines of code that would just like keep writing to disk and measure, like just figure out how long it took to write to disk. Because it's pretty simple and could do it slowly. And every few hours there was a spike, or writing to disk took a huge amount of time. And so I went, and this was an intermittent problem, and it was just a test environment, and like I sort of didn't follow up because I had other things to do. But eventually I talked to someone about this, and he's like, well, we write those data files to disk every few hours. It's like, okay, but we do that in production too. And I talked to someone else, and I learned about how these particular servers had been set up. So I guess the files that got written were like gigabytes upon gigabytes of data that got dumped down to disk every few hours. And this was like the airline fares and stuff. And in production, up until that point, we'd used hardware machines. So like you'd have a computer with a hard drive, and you just like copy the files to each machine. That'd be great. This test environment was the first time the company had used virtual machines. And the virtual machines file systems were on a network file system server, a NetApp. And so typically you'd be writing like a 5 gigabyte file to, 100 machines, each with their own hard drive. In this case, you're writing a 5 gigabyte file to a bunch of virtual machines, all of which are in the end writing to the same network file system server.
Ow.
And so now what happens is the buffers on the network file system fill up. You can't physically write to disk that quickly. And so that the buffers on the virtual machines get filled up on the operating system level, and suddenly writing anything to disk takes a really long time.
Wow.
So that explained why the logs weren't there and why the disk usage was spiking. That didn't explain why the queries weren't being answered. And so I thought about it, and I realized that the server we were using was based on, at the bottom was an event loop. So the way networking event loop is, you have like a system call like select, the classic one on Unix. These days on Linux, it's epoll, and Windows, it's IO completion ports. And basically, you have this loop where it says, wait for the next event forever. When an event happens, you handle it. In this case, you pass it to a thread pool. But if you do anything in that thread with the event loop that takes a long time, like writing a log message to disk that's going to take 30 seconds to write to disk, your event loop is going to be frozen, and you won't be able to handle any new queries until that stops. And so the problem was, like, the event loop was logging to disk. Logging to disk is usually very fast because it doesn't actually wait. It just puts it in memory, and then the operating system flushes it in the background. But in this case, all the buffers were full. And so for 30 seconds, you could not handle any requests from the network because the disk was too slow. So I went to the team that was running the server, and I said, hey, I have this problem. Have you considered not writing to disk directly in the event loop thread? You can sort of put the log messages in a queue, read from the queue in another thread, and that other thread can write to disk. And if that other thread blocks, it won't affect the event loop, and the networking will continue working. But even if disk is slow, then you'll be able to handle queries. And the head of the team tells me, oh, we already did that. It'll be out in the next release.
Did you ask him to return Guido's time machine?
Yeah. So this is like, I had to talk to a bunch of different people. Like, partly this was like a system design issue, and partly it was about the state of like the architecture, and partly it was about like this design issue. And I guess logging was a little bit helpful here, but I also could have just done nothing and the problem would have fixed itself.
Or maybe. I mean, that works until we assume that it's going to work, and then it doesn't work. Two interesting things out of that story, then, that I realized. One is that, ironically, logging was actually indirectly creating the problem. Although it wasn't really logging itself, it was the architecture, but it was logging was what was.
Yeah, it wasn't quite the logging. Or I guess it was sort of. It's a reasonable assumption that writing to disk is going to be fast, except when it isn't. So, yeah, like if you do logging wrong, you end up with. There's a variety of failure modes, and this is. If you're doing something where latency matters, it's a thing you have to think about.
Yeah. Well, the other thing I find interesting is the fact that you effectively read the negative space of the log to figure out something that was going on. You know, we think about logging in terms of what we are saying, but sometimes what isn't there is equally helpful.
Yeah, although, I mean, the common case is the thing you want to know isn't in the log because no one logged it. But yes, and there's bugs that are bad, and there are bugs that are expensive, and there are bugs that are trivial. The most annoying bug, so like I had this problem once where like I ran a process, all the processes die, there's no output. Like, it's supposed to be reading in these large files, processing them, writing them out. There's nothing in the logs. There was an error on standard out or something, but it was meant nothing. So I run the program again, same result. Like, it's just things dead, no logs. So based on the starting point, this is the most annoying bug ever. Like, what do you think the problem was?
Well, I mean, deadlocking somewhere would be the first thing I would wonder, is if it was just like resource starvation or deadlocking. Like it's running, but it's just doing nothing because it's waiting infinitely on something.
Yeah, so that's one thing it could be, but in this case, all the processes are dead.
It just crashes then.
Yeah.
Maybe an issue with operating system?
Operating system is fine. The problem was the disk was full.
Huh?
When the disk is full, you don't get logs because your disk is full. None of the software can handle it because, like, if you think of, like, you're writing software that needs to write something to disk. Like, if you get an error writing to disk, what are you going to do? Like, you can't fix it. So worst case, you'll write a log message saying, hey, I couldn't write to disk. And so full disk is like, it's extremely frustrating as a bug because, like, you have nothing. You just have to prevent it in advance. You can't fix it. You can't recover from it. Like, you might have no diagnostics at all. So
servers fail in funny ways, and then we don't find out about it until it isn't responding to something or whatever. Yeah.
So that's another case where, like, lack of logging is more indicative than the logging itself.
Well, then I imagine too, if there's conclusions to draw from logging and from lack of logging. I know a lot of people write logs, but then they just leave them there and they never read them.
Yeah, so I've been playing with some of the new sort of, I guess, observability is the buzzword tools. Like, I've been playing with Honeycomb, and what they do is they take open telemetry data, so trace-based logging, like Eliot, like trees of spans, and they let you query them. They let you have, like, fixed queries. You can, like, do derived data, and so you can have things like, show me all the queries that the 99th percentile elapsed time was higher than this much, or, like, let me zoom in and find outliers. And so instead of just a pile of text, it's a thing you can query and analyze and build fixed queries from, and potentially even get alerts on.
Right, which I can imagine is pretty important, because otherwise you kind of get this give and take of, okay, well, if you put enough detail in the logs to make them useful, and there's too much information to parse through visually, and so being able to query like that makes sense. Because I'm trying to remember the last time I actually read logs for any reason other than debugging. I know that's not great because it defeats the purpose of the logging. I mean,
it is one very important use case, but, like, another one is, which specifically if you're using something like Eliot or open telemetry, is that you can get, like, sort of rough performance metrics. Because log messages are like, this thing happened, this thing happened. Like, it's just points in time. Once you have spans, you have elapsed time. And so just you can see the different elapsed times of different parts of your program. And so you just inherently now have things you can analyze and query in terms of performance. And these days, I'm mostly interested in things that are more batch jobs or like data analysis or data processing tasks, which have a beginning and an end. Unfortunately, these tools tend to be more designed for web applications. So, like, assuming you have an HTTP response code or just the kind of queries they want you to do are very tied to, like, we had a downtime in our website, or our website's suddenly really slow, which is sort of a bit different than the kind of analysis you do on batch jobs, but the general tooling is still extremely useful in that case. But that sort of may or may not be something you care about, like, depending what you're doing, and the debugging value of logs is always there, and that's a thing that is much harder to get from other tooling. Like, you can get performance from profiling, and it's sort of logging profiling or sort of give you different information about performance that works well together. But debugging information you can often only get from logging.
I think I heard something about you and pumpkins. Can you tell me more about that?
Yes. So this is an important life lesson that I learned, is that you don't put pumpkins on the ground in your house, or watermelons, same problem. Because we bought a pumpkin in the fall, and we had it in the kitchen temporarily on the floor, walking around barefoot, and I sort of kicked it by mistake. It was very painful. And for the next 2 days, I'm sort of limping around, like, barely walk, like I'm in extreme pain. And so after 2 days, I'm like, okay, this isn't getting, I would have expected the stub toe to get better. So I look at my toe again, and it's kind of like, it was pretty bad, like there was some blood in there and stuff. And I noticed there's an orange thing in my toe. And I had noticed just for a second when I initially stubbed my toe, I just ignored it. And so this time I actually looked at it and, like, oh, there's a piece of pumpkin underneath my nail.
Oh.
Stabbing me every time I walk. And so I pulled it out, and it suddenly hurt a lot less. And I was able to walk just fine. So if I'd paid attention to the tiny bit of orange I'd noticed and just ignored 2 days earlier, I would have had a much more pleasant 2 days. And so, as with pumpkins, you shouldn't put them on the floor, but if you do, these things happen, you should pay attention. So, like, yeah, if you have logs, that's great, but the second step is actually paying attention to those logs. And I have on occasion, like, encountered significant bugs where I'd sort of seen them in the logs and I'd sort of waved it away, and later it turned out to be a serious bug. So, and I can give an example if you're interested.
By all means.
So I was working on a scientific computing project as part of a company doing spatial gene sequencing. And so there could be this microscope, and it would take pictures of sort of a cell culture or some tissue and sort of build up a 3D volume of pictures of the cell. There were lasers involved.
Ooh.
And one of the things you had to do was line up all these images. It's like, you take pictures of different slices, and, like, things could shake a little, and so things weren't exactly lined up. So you needed to sort of line up all the images so that it would be all the layers lined up exactly, which is involved a bunch of algorithms. So I had noticed some weird results, but I thought that was because it was, like, logging from a test, but the test was with synthetic data, and so I just sort of ignored it because it's just synthetic data, so it's probably fine. But then after a certain point, I realized that the algorithm that was supposed to be lining things up was just not working. It wasn't doing anything. It was garbage. So I went through the logs, and then you mentioned you're using Eliot for scientific computing. So this is the point where I started using Eliot for scientific computing, and I found it extremely useful because you're doing all these calculations, and you have intermediate values, and you want to get some sense of whether your calculation is right or not. And so if you just look at the output and the input, like you'll have no way of knowing that everything went correctly or not. Scientific computing is a extra difficult domain because you don't necessarily have a correct answer. So like if you're doing tax calculations, like you go and get an accountant and you have them calculate the same thing and then you compare your calculations, and if they match up, then your code's probably correct. Something like that. Like you have some source of truth you can rely on. And in a lot of domains in programming, that's true. But here it was like the final outcome was which genes are expressing in which different cells. It was like spatial gene sequencing. And there's no correct answer because like this is like cutting edge technology. Like there eventually got bought by a competitor, but this is all like extremely new, cutting edge. You didn't have answers.
Yeah, if you had the answers, you wouldn't have needed the code.
Right. Like, so you could tell if things were really wrong because like the biologist would say like, no way are 70% of the genes that. Like, that's a rare gene, so something's wrong. But like, you don't know really if your answers are correct. It's hard. But something was wrong. And having intermediate results at least let me spot things that weren't like the algorithm being insufficient, just me implementing it wrong, which was the problem here. And so it turned out this one intermediate number was always the same. It was supposed to be picking one of the slices in the 3D volume as the one that was, for some reason, like was best at something, had the most information or something. But it was always picking the last one. And I could tell that from the logging because I always logged which one got picked. And so instead of like it being, sometimes slice number 7, sometimes slice number 15, it was always the last one. It turns out that this being Python and indentation matters, I had the thing that was supposed to be at the end of the for loop had been dedented and was only running once after the for loop.
Oh.
So I was only ever adding the last. I was basically saying, calculate this value for each item, append it to the list, and then get the minimum. But I only ever appended the last value because of a combination of indenting things wrong and the fact that Python leaks variables from for loops. And so it was only ever getting the last value. It picked the minimum of one value and always gave that value. So like 4 spaces and the code was completely wrong. And logging did show that. Like once you looked at it and you're like, oh, I keep getting only the last value. And if I had paid attention earlier, I would have, on the test data where I was getting that, I would have fixed that and wouldn't have had to waste a bunch of time debugging it and looking at broken data. So yes, in addition to logging things, you should also be reading the data. And even if you don't have a particular bug in mind, partly it's because you end up building a model of what things should look like. Like human brain is extremely good at spotting patterns. And so, but you need to feed it information for that to work. And so if you read the logs of your programs on an ongoing basis, then you'll sort of start noticing patterns. And then if you're lucky, one day you'll say, wait, that's wrong. Or that's an outlier. Or in this case, why am I always getting... Because looking at one run, you wouldn't have been able to tell that it was necessarily that it was wrong. You were just looking at a bunch of runs and saying, why is it always giving the last value?
Yeah, why is my random number generator always outputting 15?
Yeah, and then, but you need to like see a bunch of information over time to sort of learn that. And if you just log and only look when you log and only look at the logs when there's problems, then you won't be able to do that pattern recognition. And this is also why tools that give you visualizations are so important, because you can get sort of it's much easier for people to, unless you have some sort of vision disability, seeing patterns is much easier if you compress them into an image. Yeah, like the biologists could look at a cell and say, like, there's that part of a cell, and there's that part, and there's that part. And I'd sort of see it, but, it's also just a bunch of blobs. Right? And in this case, like, by the end, I had a really good model of, like, where the kinds of noise that these images had and sort of how one would sort of express the fact you want to get rid of them. And this was all, like, just from looking at the images a lot. Like, if you later on, it's got switched to people who actually knew optics and physics, and their model would have been in many ways more accurate because they could build algorithms based on actually understanding the physical mechanisms involved, where I was just sort of throwing something together. But even just with throwing something together, just staring at these images a lot meant I sort of had pretty good model that I couldn't necessarily explain in words very well, but allowed me to write software to analyze images that worked at least decently well.
Today's special is a salted caramel macchiato. And I was thinking... Annie?
What? Oh, sorry, Jess. I'm trying to figure out how to transfer this unicorn horn to Bojan.
Do you really think that's such a good idea? He can get a bit enthusiastic.
Maybe, but he always means well. The unicorn will be back tomorrow anyway. I just don't know if I can take one more night of turning my home furnishings into root vegetables.
Fair enough.
Can you tell me more about Linux, logging, performances, and all the cool stuff that's centered around it? I'm sure you have some cool stories to share with that.
Sure. So, as I said, like one of the nice things about logging systems like Eliot or all the open telemetry stuff is that you get information about performance of your software that just comes inherently from the fact that it's span-based. And so one of the coolest tech demos I've ever seen, and this is, I think, predates the time, I believe it predates Google publishing Dapper, which is sort of the, I believe was the ancestor of all the open telemetry and similar systems. Like, I think it was just sort of the first sort of publicized system that worked that way. And this demo was before this. It was from the sort of chief scientist at the company I was working at the time. It was sort of a side project of his. And so he built this tracing system for performance, mostly with a goal of performance, but also for debugging, which is basically equivalent to Eliot or open tracing. And he built this demo. And the demo was he built a Scrabble solver. And so this is a distributed Scrabble solver running on like virtual machines in the cloud. And he's like, okay, where's most of the time taking? And using this information, this logging, and a completely generic GUI, he just broke down step by step until he figured out that it was the code that was dealing with finding the words for a particular set of tiles in the game, but only when you had 2 or more wildcard tiles. So in Scrabble, you're trying to assemble words from tiles with letters on them. There's some wildcards. And the performance problems only happened when you had like 2 or more wildcards. And that was like the most expensive part of the program. And he was able to figure that out from sort of generic logging with a generic GUI to search through the information. And this is where logging is, or tracing-based logging, at least where you have the spans, you can extract this information. And this is where it can be extremely useful for performance, is that you get sort of a big picture structure. These different parts of my program are the ones responsible. But also it's not averaging the information across different inputs necessarily. He could actually tell which inputs cause the slowness. And profilers are extremely useful in other ways, and we can talk about that. But a profiler will say, this function is where most of the time went. And that's extremely useful. What it won't say is, this function is where you spend most of your time, but 99% of the time it's slow and 2% of the time it's fast. Like, depending on the profiler you're using, it can't tell you that. It does not have that information. And so trace-based logging can give you that information of, these particular inputs are the ones that cause the performance problems. The downside is that, as we said about logging, you only get logging for places where you explicitly put logging. If you didn't put logging there, you're never going to hear about it. You've got nothing. And so it can be very useful if you have all the logging you need, and you probably don't have all the logging you need. Like, the typical experience is like you have a problem, like when you're debugging, it's always like, I wonder what the logs say. And the answer is, I neglected to put a log message there. And then you add it, and But you can't put logging around everything in the end because it just makes your program too slow. And I've done that. I've said, we should log the configuration, the state, and every operation. It was very useful for debugging, but the state was too big and it would just slow things down. And so you have to, at some point, you have to say, we can't log everything. And the large-scale systems will do things like sampling, but in the end, if you have a latency, like if you have to finish a request in a certain amount of time, you don't want, if you're sampling 1%, then 1% of your queries will take too long if your logging is too expensive. So you can't log everything. And so you need other ways to get information. And profiling is sort of very complementary because it can't tell you what the inputs were necessarily that were causing slowness, but profiling will tell you, you don't have to tell it which functions to measure. It will just say, these are the slow functions. And so profiling in production is sort of really great complement to logging in production when you care about performance.
Well, you mentioned that you can't log everything, and I know that traditionally the suggested answer to that is, we'll just have logging levels. And so we could say, this is a debug level logging, and then this is info level logging, and this is production level logging, and then you just change that. And so if you want all that information, you go to debug level and observe. But some stuff I've read from you, it sounds like that's not the best approach.
Well, so let me give you an example of a performance and memory problem I found. So this was the same company doing scientific computing. There's a bunch of image processing algorithms. It was running kind of slowly. And so it was in the cloud, so it also costs money. So I went to management and asked, what's our budget for cloud computing for everything we process? And they told me the sum, and then I did some arithmetic on the input sizes we expected once we were in production. And we were spending, if we continued with my software as is, we would be spending 70% of our revenue in cloud computing, which is bad. There's no profit, but there's also probably not enough money for my salary. And we were in tests, and so I'd never thought about performance. It wasn't the problem in the short term. This was sort of unacceptable in the long term, so I had to speed things up. And so I spent a bunch of time profiling, and this is one of the motivations for me to implement I've been working on. I have an open source memory profile I wrote, and a SaaS I'm working on that gives you production grade memory performance profiling. They're both in part motivated by this experience because the tools were not quite adapted to the tools either didn't exist at the time or weren't adapted to this use case. But I was, I got it to work. And so one of the things that was slow was, so we have to line up images. And so there was a bunch of operations where you would shift an image a pixel and a half. And because it's a pixel and a half, you have to do some interpolation. And so there's different ways you can do it. There's linear interpolation, cubic interpolation, if you ever use Photoshop or some other tool. These are options. And the linear one does a worse job, but it's much faster. And the higher, the quadratic and cubic and whatever, are slower, but give you more accurate information. And changing the interpolation level from 3 to 2, it's a one character change. Massively sped up the results and massively cut memory usage, which is also important for cloud computing costs. Because we were able to, if your ratio to memory to CPU is not right, then now you have to get a special sized cloud instance, and memory is expensive. So I was able to cut memory and CPU usage dramatically by just slightly reducing the quality of the interpolation when you did subpixel image shifts. And logging sort of gets you there, but I would have had to have a logging on every line of that computation to actually know that was it, because you're doing a series of steps, and you can't really log every single line of the algorithm. It becomes unreadable. There's too much overhead, and in some cases you're calling out into third-party libraries. And someone who's implementing, I was using scikit image. People who are implementing scikit image, they don't put logging inside their algorithm implementations. They don't really have a reason to do so. And so logging would have gotten me to this particular part of the code is slow, but to sort of localize it I needed both profiling to get, oh, it's this function, and then additionally, like, sort of saying, oh, maybe if I did worse quality, I can get it faster. And it did impact the results a little. I got like 0.5% worse results in the final outcome, but 0.5% less on, whatever it was, cutting the runtime in half. I don't remember exactly, but like the payoff for reduction in quality was massive. And yeah, it's especially once you're dealing with third-party libraries, like they have definitely not put logging on every line.
So a lot of it is identifying kind of that question of what do you really need to log? Because, ideally you need to log everything, but practically you can't log everything. And so it sounds very similar to the logic that goes into like with performance, where you're saying, performance, first of all, any performance gains are mythological until proven. And second being, don't optimize the parts of your code that don't get run very often. You want to optimize the hot path, not the cold path. Otherwise, you're just wasting effort. And it sounds like logging kind of operates on a similar principle that, well, yes, ideally we'd like to log everywhere. Just like, yes, ideally we'd like everything to be high performance, but performance considerations in mind, we have to pick our battles.
Yeah, so I want to get back to you focus on the hot path, like certain, like memory usage is an interesting kind of performance where in some cases it acts very differently than performance and sort of interesting and so the way you prioritize. But in terms of logging, in one situation where I added logging and it had made things too slow, a coworker explained the process they went through at her previous company, where they very explicitly went through this process of add like massive amounts of logging to as much places as they could. Like they would add a huge amount of logging during development, and then they would, as they got closer to release, they would start measuring the code and getting the performance impact, and then they would have this process of removing logging over time. So they had this very explicit process of, we are deliberately going to add logging we know is not going to last. And they would add it, and then once the use of it for debugging or development was less strong, because they were fairly confident in the software, then they would do another explicit pass of, okay, which of these logs do we think are too expensive? And so we're going to remove them before we do the final release. And so, as in a lot of things in software, there isn't necessarily a good... The answer is usually situation specific, but a good process is very helpful.
So it's avoiding premature optimization. You're not optimizing your logs prematurely. You're optimizing them on the basis of measurement and actual observable need.
Yeah. And so, like in the scientific computing case, I tried to log every There are some domains where like extra logging is almost never very expensive. Like I was trying to log basically all the intermediate numbers I calculated. Because like the actual calculation itself would be vastly more expensive, because this thing would run for hours, right? So it's very difficult to get high performance overhead from logging when like the actual process runs for hours, as long as you're not like logging the actual like large arrays or whatever. And same for data science. I would love someday if someone were to build a system that actually did let you say, I'm going to log this array that's halfway through the process, or I'm going to log this data frame that's halfway through the processing. I think there are ways to do it. None of the services that are doing like open telemetry are, as far as I know, like really is the thing they think about, because like they all care about like web applications and things like that, which have very different characteristics. But with the right infrastructure, I believe like even with like data science or scientific computing, it would actually be possible to log like really quite massive amounts of data without significantly impacting performance in some architectures, and depending what libraries you're using. And don't have time to build it. I would love if someone else did, though.
If only we had infinite time.
Yeah. I have a question. You mentioned a lot tracing and logging, and for me they seem interchangeable. Can you tell me what's the difference between them?
So logging is maybe the more general purpose term, but like if you, in Python, which language I've used most, these days I'm doing some Rust, but pretty much any language, there'll be a logging package. You import the logging package and you say logging.info, hello world, logging.info. I started the thing, logging.error, oh no, it didn't work. And so each log message is sort of this isolated event. And you can say log message level info, I started, and later log level message info, I ended this thing. And those two messages in theory connect, but like they're not, there's no infrastructure really to connect them. They're just two statements which you as a human have to read. Maybe you can start building infrastructure where they have like some metadata, but like the basic, most logging libraries that call themselves logging libraries, you just have these messages. One message, another message, another message. And tracing is more like Eliot or OpenTelemetry, where the unit of abstraction is not the message. The unit of abstraction is a span or an action. So you have a beginning and an end, and a tree of these spans. And so when I say tracing, I'm talking about that sort of tree structure of spans that say where I started doing this and I ended doing this is semantically expressed in the actual output. You don't have to sort of retroactively try to figure it out. It's just that's the abstraction you're working with. And so in Python, you might use a context manager to say with start span, and then when the code finishes, it automatically would close the span. Or you can make a run in span, and then you give it a closure or a function, and then when the function it starts the span when the function finishes. It depends on your programming language what the idioms would be, but tracing is that tree of spans or tree of actions that have elapsed time. And that's what gives you the performance information. That's what gets you causality. That's also that you trace things more easily across different systems because you can sort of, the tree in one process can be connected to the tree in another process.
How do you write programs with better performances? You mentioned that your SaaS is focused on that. And I really want to pay less to AWS for cloud hosting and computing. So how do I make my code run faster with the less resources?
Yeah, so the answer, as usual, is it depends. Any sort of advice is always about the context and situation, what kind of problems you're dealing with. So the things I'm interested in these days are data analysis, scientific computing, batch jobs, which are different than web applications in a bunch of ways, and that they tend to run much longer. They use significantly more data. So memory usage tends to be more of a problem, and the ways in which memory usage is a problem are different. And they have a beginning and an end. And so you have this structure of, I'm going to load some data, I'm going to process it, and I'm going to write it out, and I'm done. Whereas web applications, in some sense, run forever. Just keep handling queries. And so there's less, you can think about individual requests handled by the web application, but like it's not, they're tiny and like they're not really, they're usually too small of a unit to think of unless you are optimizing for latency really closely. So in sort of thinking about, that domain, which is what I'm interested in, avoid early optimization is a thing people say, like quoting Knuth, who famously early, premature optimization is the root of all evil. That's, you probably shouldn't make all your decisions based on someone's quote. And if you do decide to do that, it's probably worth looking at the context. And there's a bit more context there. But if you were to naively say, okay, I don't have to think about performance, and you just start writing some data analysis or computation in pure Python, your code's going to be really, 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 really slow. Python's ridiculously slow. And so there's all this infrastructure that's been built up for Python, which is one of the most commonly used languages these days for scientific computing and data analysis and data science, even though it's so slow. And that's based on particular idioms and particular library designs focused around vectorization, where you say, we're going to do these batch operations, and that operate on the whole, like a whole array or a whole data frame or a whole column in this data. And the underlying data structures are designed to be amenable to fast access from a language like C or C++ or Rust or Fortran, depending. And then the Python is basically gluing together like fast operations that operate on a whole array or whole data frame, and so on. And so the only reason Python is usable is because of this sort of set of libraries based on a set of insights and a set of design patterns for how to structure a code. This isn't premature optimization. It's sort of just like, if you didn't do this, no one would be using Python. The reason Python is usable and is used for so many in so many of these domains is because a bunch of people went and wrote some libraries to make this happen, starting like back in the 90s and then building on that. And so if you know performance matters, you have to start thinking about performance from the start. And that's one part of it. And the second part is that implementation matters. If you think about, you want to sum some numbers, a list of numbers, which is the thing you do a lot. You're doing math. You can have a version that's using just a Python list and a Python for loop, and it just takes Python objects and their numbers and adds them together. And you can do it. You have a NumPy array, which is basically just a C array behind the scenes. And when you do, sum on that, and behind the scenes, it's just calling some C code on the C array, and that's fast. The number you get back in both cases is the same. Right? There's no semantic difference between the two. But the implementation is fundamentally like just 2 orders of magnitude different. Like we were talking about earlier about the bug where logging stopped and then the whole process stopped. Right? Writing to a file might be immediate, and most of the time it is. Occasionally, though, it'll be extremely slow. In terms of the semantics, like unless you're like worrying about like crashes, like if you don't have to worry about like crashing halfway, it doesn't matter if it writes immediately, it writes later. Like you don't care if like your logging thing writes to a queue that logs it later, or writing directly to disk, as was the case here. But the performance implications can be huge. And so performance requires you to sort of peek behind the abstractions. Like you can't say, oh, this is, there's an abstraction layer here. I don't have to think about how it's implemented. I'm just going to use it and things will come out. You have to have some knowledge about what's going on. And if you're lucky, someone gave you an abstraction that's really well designed for performance, and then you don't have to think about it. And all the data analysis and scientific computing libraries for Python have tried to do that up to a point. But even there, like you hit these edge cases where in order to use the fast operations, you have to like transform a whole array instead of using a for loop. And so now it's fast, but now you've created a whole copy of the array. And so suddenly you've just doubled your memory usage. And if that's like a gigabyte array, that's pretty meaningful. And so even in the cases where the libraries have done a good job of usually hiding these issues from you, like they're usually not perfect. And then you hit these cases of, oh, if I want to do this memory efficiently, I'm stuck with slow Python. If I want to do it fast, I suddenly double my memory usage. And which do I choose? In this case, there's a third tool that will solve it. But again, all of these 3 implementation choices will all give you the exact same result. It's the implementation trade-offs, how they're implemented, that really matter, and performance. Like you can't just only look at the abstractions.
Well, it reminds me, there's been a lot of times where when I've been designing a system or whatever, and I start thinking about some of the stuff early on, and I hear the same phrases all the time from people who are observing my work. It's like, well, there's the, premature optimization is the root of all evil thing. We hear that bandage about, like you mentioned. The other one is Yagni, which makes my blood run cold because it's a nice idea and practice, but it leads us to do some rather silly things as well. Because in both cases, the way I always explain it is I'm not implementing it right now. I'm just keeping it in mind so I don't code myself into a corner. I want to enable myself to implement this optimization later. I want to enable myself to implement this feature later. I don't actually have to write the code right now, but I need to make decisions such that I am able to write that later, as opposed to coding it in such a way that it's not possible to write or not practical. for that matter.
Yeah, and I mean, premature optimization is sort of a fun phrase because how do you know it's premature? Well, you shouldn't be writing it. And then you say, well, you shouldn't do the right things you shouldn't write. Like, it's sort of, the word premature in there is doing a lot of work because premature means you're doing it too early. Like, so don't do things too early.
Yeah. Well, it's just like Yagni is basically, both of them are forms of the fortune telling bias. Like, well, I predict in the future that, and so because you can look back and see, oh, I didn't need that, didn't mean that looking forward you can see that you don't need it. It's not always as well. I guess the biggest takeaway is don't pass judgment on someone's architectural decisions early in the game because if you're just observing because you can't see the future. You don't know what all is in that developer's head.
Yeah. And I guess as a adjunct to all of this is that on the one hand, performance is hard to predict. Like in the end, like you need tools to measure it because like you won't always know. And sometimes like memory usage is one of these things where like it's so easy to mistakenly just do something tiny and suddenly your memory usage has exploded when you're dealing with like things that are 10 gigabytes of data. Like, because copying something that's 10 gigabytes of data and copying something that's like 100 bytes are the same line of code. Right? They don't look any different, but one has very significant impacts. So you need measurement, but a lot of it is just thinking about it. Just saying, okay, I'm going to spend some time to understand how things work. I'm going to spend some time measuring. Like I'm going to think about it because you can learn new skills and you can learn new ways of thinking. You can learn like models of how the software abstractions under you work down to the CPU in some cases. And like there's always more to learn, but like anytime you go down one abstraction level, say, I'm going to figure out how this is implemented. And you can sort of build these skills over time of just being better at writing fast software. And so part of it is just saying, I care about this, and I'm going to spend a little bit of time learning, a little time building my skills, and a little bit of time measuring. And if you do all that, you can write faster software from the get-go and architect it better from the get-go. So it takes some work, but it is a thing you can do. And fast software is sort of inherently more fun to work on because you have a faster feedback loop and saves money, and you're pumping less carbon into the atmosphere because computing is a huge amount of carbon emissions just because you use so much electricity. So like, writing efficient software is more fun, costs less money, and good for the environment. So I think it's worth doing.
Thank you. Learned a lot about logging and performance.
It's great meeting you and hanging out here.
And hey, Bojan, I just noticed they just opened up a new thing of pumpkin ice cream. Anybody want some pumpkin ice cream? Perhaps maybe we can eat the pumpkin that attacked Itamar in effigy.
Yes.
We did actually carve it up later with a knife.
Oh, good.
But that was the plan anyway, so maybe it was just preemptive revenge.
Absolutely. I'm going to go get some of that ice cream. I'll be right back, y'all.
Hello, Bug Hunters Cafe. This is Jess. Well, we're always open 24/7 at bughunters.cafe, and you can also find us on Twitter as Bug Hunters Cafe. The music? Yes, it's provided by audionautics.com. We have a link on our website. Sure thing. Have a great day.
Okay, Bojan, I finally found the instructions for transferring the horn to you. Are you sure about this?
I've never been more ready for anything in my life.
Okay, here goes.
Did it work? It did! I have my very own unicorn horn. Now I can transform anything I want into ice cream.
Oh, that isn't what that's for.
You're back early.
Wait, no. 5 more minutes. Oh, there goes my horn.
Listen here, Unicorn. Next time you get the bright idea of giving someone a magical horn, at least have the decency of asking first and providing some training.